Hello there, welcome to video 2-8, and we are going to talk about the quotient rule today, as well as our final trig derivatives. So we'll start out this video looking at the trig derivatives, and then I'll introduce you to the quotient rule. Alright, previously in 2-6, we went ahead and learned that the derivatives for f of x of sine of x and f of x equals cosine of x, we learned those trig derivatives. Now we're going to go ahead and talk about the remaining four. So here are the trig derivatives, and again, we have already went ahead and found the derivative of sine of x and the derivative of cosine of x. And now I'm going to go ahead and introduce the other ones. So if my function is tangent of x, well, the derivative of tangent of x is secant squared of x. Secant squared of x. And then if I have the function cotangent of x, the derivative of that is negative cosecant squared. Okay, and then the last two, f of x is equal to secant of x. Well, the derivative of secant of x is secant tangent of x. And the derivative of cosecant of x is negative cosecant cotangent of x. So those are the remaining trig derivatives. And what I want you to do right now is to pause the video. I would like you to go ahead and see what patterns you notice. There's a couple of patterns that can help you remember these trig derivative functions. Okay, so go ahead, pause me, try to figure out some connections or patterns. All right, hopefully you went ahead and noticed some patterns. The first one that you should have noticed is that the derivatives that begin with a co, well, all of their derivatives have a negative. So I'm going to say here, okay, kind of pattern number one, derivatives of trig functions, I'll abbreviate that, trig functions with quote-unquote co are negative. And hopefully you picked that up here. Notice, every time I take a derivative of a cosine, negative sine, derivative of cotangent, negative cosecant squared, derivative of cosecant, negative cosecant cotangent, okay? So that's pattern number one. And you should also notice, too, that there's some connections. So we have cofunctions, functions that are connected. So like here, tangent and secant, they're often paired together. So the derivative of tangent is secant squared, and the derivative of secant is secant tangent. Well, the derivative of the cofunction with tangent, cotangent, it's the same structure. It's a negative cosecant squared. So instead of secant, it's cosecant. And then similarly, if I take the derivative of secant, that's secant tangent, and the derivative of the cofunction was secant, cosecant, well, its derivative has the same structure. It's a negative, and it's cosecant cotangent. Okay, so you should have went ahead and noticed that, and I'll spell out number two for you. So it says trig functions appearing in a derivative are the cofunctions of those in the cofunctions derivative. Okay. All right. So I also recommend, again, we just got 4 new derivative rules, okay, the other trig functions. So again, I recommend making flashcards. Make your flashcards where you put one function on one side and then the derivative of it on the other. Okay, so let's go ahead and see how this is applied. Example number 1. let y equal x cubed tangent of x. Find the slope of the line tangent to the graph of y at x equals pi over 6. Okay, so I need the slope of the tangent line. So that's going to be y prime, and they want it at x is equal to pi over 6. Okay, so well, what I need first is I need to figure out, okay, what's y prime? So y prime, x cubed times tangent of x. Well, hey, aren't they multiplying? That's product rule. Two functions multiplying. So the derivative of the first, 3x squared times the second, tangent of x, plus the derivative of tangent. Oh, the derivative of tangent. Well, we just did that one. Tangent is paired with secant, and the derivative of tangent or cotangent, it's always the other function squared. So secant squared x times x cubed. Okay, there is my derivative. Now what we need to go ahead and do is we need to evaluate at pi 6. So 3 times pi over 6 quantity squared times tangent of pi over 6 plus pi over 6 cubed times secant squared of pi over 6. There you go. There is the slope. That's pretty gnarly. You could go ahead and plug that into a calculator, but our values would be 0.6662. I'm going to include the 2 just so I don't feel evil. All right, so there you go. We'll encounter more of those trig derivatives as we go on, but in this part of the video, now we're going to go ahead and we're going to talk about the quotient rule. So here it says, in example 1, we use the product rule to differentiate. And just as some functions are a product of two functions, we will also work with a quotient of two functions. As a result, it's convenient to have a derivative rule for these cases. So if I have a function where I have two functions being divided, f of x divided by g of x, well, the derivative of h prime of x is the derivative of the top, f prime of x, times the bottom, times g of x, minus the derivative of the bottom, g prime of x, times the top, f of x, divided by the bottom squared. So here we have g of x, and this whole quantity gets squared. That is the quotient rule. That's the quotient rule. Okay, so we're going to go ahead and make a couple of notes about this. Remember, in calculus, we only take one derivative at a time, one. And then here too, they say we can express this in terms of u and v. So if it's u and v, right, it's going to be u prime v minus v prime u all over v squared. All over v squared. And I'm not a total fan of u and v. That's very applicable, especially if you're in Calc BC. The u and the v will be important, but my favorite is to go t and b. So t over b prime. And again, the t just stands for the top. So the derivative of the top times the bottom minus the derivative of the bottom times the top divided by the bottom squared. So that's the derivative if we are dividing two functions. Okay, this is another item for your flashcards, so put that on your flashcards, rotate that one in. And then point 3 here is that order matters, especially in the numerator. You have to go ahead and you have to take the derivative of the top times the bottom first, and then also watch for presentation errors in the denominator. So make sure if you're plugging in a binomial that you square that whole binomial, because you don't want to, write it incorrectly. Okay, let's go ahead and let's apply this. Example number 1. Find dy dx if y is equal to 5x minus 2 over x squared plus 1. What you need to see is I have one function being divided by another function. And that's very, very important. One function being divided by another function. So I have multiple inputs, right? Multiple x's. So something I did in the product rule video. Again, you can identify, hey, what's my top? 5x minus 2. Okay, what's the derivative of the top? 5. Okay, and then what's the bottom function? X squared plus 1. And then the derivative of the bottom? 2x. So if you just take the time to organize it like that, that might help you go ahead and organize your response. Okay, so the derivative of y with respect to x is equal to the derivative of the top, 5, times the bottom, x squared plus 1, minus the derivative of the bottom, which is 2x times the top, 5x minus 2, all over the bottom squared. So x squared plus 1, I'm going to put parentheses around that whole thing, and I'm going to square that entire thing. Okay, so, and if I wanted to go ahead and simplify here, let me just kind of distribute. We have 5x squared plus 5 minus 10x squared plus 4x all over our denominator squared. X squared plus 1, quantity squared, and I'll clean up that numerator, negative 5x squared plus 4x plus 5 all over x squared plus 1, quantity squared. Okay, so there's our dy dx. All right. Example number 2. Example number 2. Let f of x equal 3x squared minus 2x plus 3. Find f prime of 2. Well, here they're trying to get you. This is an Admiral Akbar moment. It's a trap. They really want you to think that you need a quotient rule here. You don't need quotient rule. I have a numerical denominator, and really, even if I had a variable in here, x, my next strategy that I can go ahead and show you also applies. So if you have a monomial denominator, and go ahead and write this. If monomial denominator put a box around that. You can go ahead and split your terms. So what I'm going to do is I'm going to say, okay, f of x is 3x squared divided by 7 minus 2x divided by 7 plus 3 divided by 7. I can go ahead and split that. This is true. I can go ahead and divide every single term by that denominator. Okay, and then my derivative is so much easier. So much easier. Even if you have a variable in your denominator, if you have one term, just split all of the terms. So here we go. Here's f prime. Not f prime of 2. I'll wait to get to f prime of 2. So the derivative of my first term is 6/7 x minus 2/7. Wasn't that so easy? Man, that monomial denominator. Go ahead and split it. Okay, and then f prime of 2, it looks like 12/7 minus 2/7. 10/7. 10/7. 10/7. All right, there you have it. All right, let's go ahead and look at example 3. Example 3, let g of x equal sine of x divided by 3x squared. Find the instantaneous rate of change at g at x equals 4. This is their fancy way of saying find g prime of 4. Okay, so g prime of x. I'm going to go ahead and take the derivative. What you need to see, I have a function in my numerator, a function in my denominator. What tool am I going to pull out of my tool belt? The quotient rule. So I'm going to go ahead and take the derivative of the top, cosine of x, times the bottom, 3x squared, minus the derivative of the bottom, 6x times the top, sine of x, all divided by the denominator, 3x squared, quantity squared. Okay, make sure you put parentheses around your denominator and square it. So, okay, I mean, I feel like, I guess I could clean up, we could do this, 3x squared cosine of x minus 6x sine of x, all over 9x to the fourth, if I wanted to clean that up, okay? And then g prime of 4, I'm just going to go ahead and plug this in. So we have 3 times 4 squared cosine of 4 minus 6 times 4 sine of x, sine of 4 divided by 9 times 4 squared. Okay? Alright, and if we went ahead and clean this up, 16 times 3 is 48 cosine of 4 minus 24 sine of 4, and 9 times 16, that would give us 153. So 48 cosine of 4 minus 24 sine of 4 over 153, I believe. 9 times 6 would be, no, 144. Okay. You can also go ahead and reduce by, I believe, 24. I believe you could reduce by 24. But we'll go ahead and call that good. Okay. So there's the analytic examples, and then now we're going to go ahead and look at the graphical examples, which again, these examples are the same idea. It's just we're getting our information, our slopes, and our function values from a graph. Okay, so they say the graphs of f and g are shown and consist of line segments. Use the graphs above to find the following. H of x is equal to f over g. Find h prime of 0. Okay, so h prime of x, that's going to be equal to f prime times g minus g prime times f divided by g squared. So g of x squared. Okay, and now we'll go ahead and find h prime of 0, which gives us f prime of 0 times g of 0 minus g prime of 0 times f of 0 over g of 0 squared. Okay, so let's go ahead and find this information. Again, I have multiple graphs, so I like to, kind of clearly identify them. So that function's f, the other function will be g, and we are looking at 0. So here's 0, and it looks like f prime is negative 1. F prime of 0 is negative 1, and our function value, f of 0, is 4. Okay, and then g prime of 0, that's right there. It looks like our slope is 2, and the function value is 5. Okay, so let me go ahead and drop these in. So f prime of 0, that's negative 1 times g of 0, that would be 5. Minus g prime of 0 is 2 times f of 0 is 4, all over g of 0 squared. So that's 5 quantity squared. Okay, so cleaning this up, we have negative 5 minus 8 over 25. So negative 13 over 25. Awesome. All right, example 2. example 2, or B, I would like you to go ahead and try this one. Please pause me. B, let k of x equal g over f and find k prime of 7. Pause me. Go ahead and I'll show you the answer here in a moment. All right, let's go ahead and look at this one, k prime. So first we got to go ahead and find k prime of x. So our numerator this time is g. So it's going to be g prime times f minus f prime times g. And we got to go ahead and square f of x. So I need to square f of x. And then we're going to go ahead and in order to find k prime of 7, we're just going to drop in those values. So g prime of 7 times f of 7 minus f prime of 7 times g of 7 all over f of 7 squared. Okay, so we need to know what those function values are, and so we're going to go to our graph. We're going to go ahead and look at this. We're going to find 7. So it looks like it's 7. Okay, here's f. So f of 7 is equal to 3. F prime of 7 is equal to 1/2. G is right above it. G of 7, that's 4. And the derivative there looks to be 1, negative. Okay, so those are the values that I need for my my function. So we're going to go ahead and drop these in. Okay, so g prime of 7, that was -1, times f of 7, which was 3. Okay, minus f prime of 7, that was 1/2, times g of 7, which was 4, all over f of 7 squared, which was 3 squared. Okay, and if you work that out, you should have gotten -5/9. All right, pretty straightforward, right? So it's nothing different than we've been working with product rule. It's just now we have a different formula, right, that we're applying for a quotient rule. Okay, C, here they say let p of x equal f of x over 3x. Find p prime of -1. Okay, so I'm going to go ahead and find p prime of x. Now, my function in the numerator is f, so f prime of x times my denominator, which is 3x, minus the derivative of the bottom, which is 3 times my numerator, f of x. Okay, and we're dividing by our denominator squared, so 3x squared. Okay, and now we'll find p prime of -1. So I need f prime of -1. I'm going to have to go to my table for that, times 3 times -1 minus 3 times f of -1 over 3 times -1 squared. Okay, so let's go ahead and see what's going on at -1 for f. So looking at f, so we have these two values. Okay, so which one's f? We need that one. Okay, so 5 is our function value. F of -1 is 5, and then the slope is -1. So f prime of -1 is -1. Okay. So I'm going to plug that in. -1 times -3 minus 3 times 5 was our function value over -3 squared, which is 9. Okay. So we get 3 minus 15 over 9, which we get -4/3. Okay. All right. Last example, here you go. We want to have let w of x equal x squared over g of x, and we want to find w prime of 2. This is an example for you. Please pause the video, and I'll go ahead and give you feedback here in a moment. Okay, let's go ahead and first take the derivative. Taking the derivative, I am dividing two functions, so I have to use the quotient rule. Derivative of the top, 2x times the bottom, g of x minus the derivative of the bottom, g prime of x times our numerator, which is x squared. I don't know why I did black there. I should have done red. X squared. Okay, divided by g of x, all squared. All right, and now let's find w prime of 2. Okay, so 2 times 2 times g of 2 minus g prime of 2 times 2 squared divided by g of 2, all of that squared. Okay, and it looks like we have, so 4 times 7 minus 0. The slope at 2 for g is 0. Okay, times 4, all over 7 squared, so we get 28 over 49, which if we reduce by 7, we get 4/7. Okay, so hopefully you went ahead and you got that function. All right, hey, that is the quotient rule. In this video, we talked about the quotient rule. We also introduced the derivatives for the other 4 trig functions, tangent, cotangent, secant, and cosecant. Use your flashcards, memorize, quiz yourself, do it consistently. All right, catch you in the next video. Give me a thumbs up, subscribe. See you next time.